Nothing says fun like watching your 3D printer turn a model into a pile of flavorless plastic spaghetti that gets scraped right into the trash can. Over the next few minutes, I'll walk you through the process of calibrating a new spool of filament for an FDM 3D printer. This includes tuning temperature, Z offset, retraction, flow rate, and pressure advance to ensure strong, clean, and reliable prints. While there are several different types of 3D printers available today, I'll be focusing specifically on fused deposition modeling, or FDM printers. Some steps may apply to other types, but I'll be drawing from my personal experience using only my two FDM machines. 3D printing has been a personal hobby of mine for nearly 2 years. In that time, I've calibrated more rolls of filament than I can count. Experimenting with different brands, colors, and materials, my experience combined with some excellent calibration guides makes me confident in helping others get great results from their own printers. The world of 3D printing is an exciting and ever growing field. With more types and colors of filament being produced regularly, it's important to calibrate some of the ways the printer operates in order to achieve optimal prints. Every filament is a little bit different. Material type and color affect the way the material behaves once it reaches a molten state. Printing a new filament without calibrating it first can become a costly endeavor. This can lead to failed prints that end up in the trash and blobs of molten plastic growing in size until they consume the entire hot end. The results do not necessarily have to be catastrophic in order for a print to be considered a failure either. Poor layer adhesion will cause the prints to become structurally weak, and incorrect temperature settings can lead to excessive stringing or blobbing. Improper bed temperatures can cause prints to shift mid print or warp on the print bed. Retraction settings that move the filament too much in either direction can cause stringing, or pockets of space where there should have been material, and blobs of extra material deposited in corners or other areas that make a print like it was made with one of those 3D printing pens. There are a few articles and guides that I've followed and adapted over time to suit my own needs. The first and most informative is the Ellis Print Tuning Guide. Another valuable resource that I have found myself referring back to on several occasions is from Instructables.com titled Perfect Prints, the Ultimate Guide to Filament Calibration. And finally, SCale7 on GitHub has a very comprehensive guide posted that will cover any additional information that you may want after watching this. Now that you understand why calibration matters, it's time to get into the how. I've recently bought a new spool of filament, an interesting shade of green PET G filament from Overture. It needs to be properly calibrated before I can count on it to print reliably. The first step in calibrating a filament is to determine which temperature the nozzle needs to be in order to achieve the best print quality. The slicing software that I use to process 3D models into a format the printer understands is called OrcaSlicer. It has built-in tools to make calibration a breeze. To begin, open OrcaSlicer and click the calibration menu along the top of the screen, then select Temperature Tower. A dialog box will appear, prompting a selection of the filament type and temperature settings for the nozzle. Every roll of filament has an optimal printing range on the label somewhere. Find that information and plug it into the fields. The slicer software will then generate a model that is printed at different temperatures across specific layers. Once the temperature tower prints, thoroughly inspect it. Be on the lookout for excessive stringing in the circular cutout areas and examine how the printer handles bridging or overhang printing areas. Smooth surfaces, crisp edges, and clean overhangs are the key here. This tower is designed to print some of the more challenging features that can be performed by FDM printers, such as printing in midair without support. For these areas to print successfully, the temperature needs to be dialed in precisely and the cooling must be effective. Only then will you get strong, clean results that you can count on. The next step in this process is to adjust the distance of the nozzle from the bed, also known as the Z offset. As I've said before, every filament behaves just a little bit differently in its molten state, and you may need to adjust Z offset just a bit to ensure that perfect first layer squish. You want the nozzle to be just at the right distance from the bed so that the filament is placed directly next to the previously printed line. If the nozzle is too close, it will grab the filament that it has already placed when it passes. Too far, and the lines placed on the build plate will not be touching at all. When printing, the nozzle comes into contact with the molten material, flattening as it extrudes. The trick here is to find that sweet spot where the nozzle is in just enough contact to bond with the previously laid lines to not interfere with them. Additional information on this subject can be found at 3dsource.com. To perform this test, I generate a 100 by 100 by 0.2 millimeter square in the center of the print bed. In OrcaSlicer, from the Prepare tab, right-click anywhere in the print bed. From the menu, hover over Add Primitive, then click Cube. Once the cube is created, click the Scale button in the top of the toolbar. Make sure the Uniform Scale box is unchecked and adjust the size, ensuring the Z size matches the first layer height. Print this square and adjust the Z offset as it prints. Make small adjustments and note the way the filament behaves as it exits the nozzle. Once you're happy with the first layer, you can cancel the print or let it finish. With the temperature and Z offset calibrated, it's time to move on to the retraction settings. Retraction is the act of pulling the filament back from the nozzle by a specified distance when the print head moves from one location to another. This prevents excess filament from oozing out during travel moves. Once again, every filament behaves differently in its molten state, so determining the proper retraction distance is key to ensuring the filament is only deposited where it's supposed to be. Retraction settings can vary depending on the printer's setup. My printer uses a direct drive system, meaning the extruder sits directly above the hot end. This allows for more precise filament control compared to a Bowden setup, which uses a longer tube between the extruder and the nozzle. Within OrcaSlicer, return to the calibration menu and click Retraction Test. A dialog box will appear where you can input a starting and ending retraction distance, along with a step value. What this does is print two small cylindrical towers side by side. Every few layers, the amount of filament retracted will increase by the specified rate. Once the test finishes printing, examine it closely. The goal is to find the layer with the least amount of stringing between the two towers. When you find the cleanest layer, count up from the bottom to determine which step it's on. Multiply that number by the retraction step size you chose earlier, and you'll have your ideal retraction setting. So far, we've calibrated the temperature, Z offset, and the retraction distance. The next step in this process is to calibrate the volumetric flow of the filament to ensure consistent extrusion and accurate dimensional prints. The Ellis Print Tuning Guide states volumetric flow rate indicates how much plastic that your hot end can extrude per second. Volumetric flow is expressed in cubic millimeters per second. We will be utilizing one of OrcaSlicer's built-in calibration tools to perform this test as well. Click the calibration menu in the top of the window, then mouse over flow rate and click YOLO, recommended. The software will generate a series of tiles for the machine to print. Each one is printed at a different flow rate. Once the print is finished, examine the tiles carefully. Start by looking for visual consistency in the prints, clean perimeters, solid infill, and no gaps or over extrusion. Then run your fingers across the top surface of each tile. The ideal flow rate produces a tile that not only looks smooth and uniform, but also feels flat and consistent to the touch. The number at the top of each tile represents the adjustment in flow rate from what it was set to. After determining which one is best, add the number to the existing flow rate value. There's one last calibration step to perform, and the new filament will be ready to reliably print. Don't worry, this one only takes a few minutes. The final calibration step is pressure advance. This setting helps maintain a consistent flow of filament while the extruder starts and stops. Printing before you've performed this calibration certainly is not going to cause the catastrophic failures that I spoke of earlier. However, taking the time to calibrate this will certainly improve the quality of any FDM 3D print. This test prints several horizontal lines with varying pressure advance values. These values are added to the print at the end of the test. Once the test is finished, examine the print. What you're looking for is a smooth, consistent line that does not have the blobbing at the start and end of the nozzle acceleration. After determining which of these lines look the best, take the printed value to its right and plug that into the flow ratio and pressure advance section of OrcaSlicer. It may have taken some time, but we got there. With the newly calibrated filament, you're ready for the final test print. I use a 3D Benchy, which is a little tugboat that is designed to stress test the printer. This final print will highlight any areas that may need to be adjusted more than they already have. Now that the Benchy has been printed, you should be able to reliably print with the new roll of filament. Let's go over the steps one more time to be sure. First, I discussed the importance of calibration. Then I covered temperature tuning. The next step is determining the Z offset, then retraction settings. Finally, determine the proper volumetric flow and pressure advance settings for the new roll of filament. Thanks for joining me in this filament calibration demonstration. I hope you learned something, even if you don't use a 3D printer.